Hello and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. Welcome to today's show. We've got a really exciting episode lined up with Dr Graham Cooley from ITM Power. It's going to be a really interesting discussion today about electrolyzer technology and the hydrogen economy. So welcome to the show, Graham. Thanks for joining me.
Hi, Ryan. It's nice to be with you.
Great. So if we could get started just by finding out a bit more about you, Graham, if that's okay. So where did you come from?
Where did I come from? I came from the power industry. Actually, I was business development manager at a company called National Power, which was the UK's largest power generator. I then became business development manager in International Power. National Power was bought by RWE and International Power was bought by Engie. So power industry is my main background, particularly energy storage. Okay,
so really big, high power grid systems, basically.
Yeah, I mean, we at National Power, we built what was at the time the world's largest electrochemical energy store. So it was called Regenesis. It was built at Little Barford, and
Little Barford.
Yeah, Little Barford, the
old power station
of the combined cycle gas power station.
Yeah.
It was 100 megawatt hours. Opened about 25 years ago now. So held the record for the world's largest electrochemical energy storage device for a long time, actually, until Elon's battery in Australia.
Oh, wow. That's really fascinating. Got some connections back to Little Barford from my I won't go into that now, but that's really interesting. You did going back a little bit earlier than that, and so obviously not that long ago, but you did a PhD at some point in the past. You are Dr. Graham, after all. What was that in, and how what got you interested in that field?
So the area was electrically and ionically conducting polymers, and it was about electron mobility and ionic mobility in polymeric materials. And of course, that's extremely relevant for electrolyzers and fuel cells, which use ionically conducting polymers as the membrane, and also for the electrodes as well. So, an interesting 3 years of R&D study.
And what sort of sparked your interest in that? Because that, back, I don't mean this to sound rude, but back then, obviously not all that long ago, but these things feel like they're new technologies, and we're probably talking at least 20 years ago, right? Maybe a little bit longer.
A little bit longer than that. So this was from the mid-'80s until the late 80s when I started with the CEGB. What sparked my interest in those materials? It was the other way around, actually. I was looking to do a PhD. I did it at Brunel University, and I liked the academic who was working in that area very much, and he offered me the role. So it was more opportunistic than planning, to be frank.
Oh, wow. Okay, that's interesting. And as a result, is that sort of what you would describe as electrochemistry? Are you an electrochemist?
Yeah, there was some electrochemistry in it. I certainly did some electrochemical synthesis of conducting polymers in that. But I think that, electrochemistry for energy storage is incredibly important. Whether you're looking at electrochemistry to produce tantalum oxide to tantalum, which is what we did at Metallicis. That was for supercapacitors. or electrochemistry in batteries, and I worked to a certain extent in batteries. But Regenesis was actually a flow cell. It was a flow cell device, a redox flow cell. So again, that was scaling up an electrochemical device.
Interestingly, because it's been literally just in the last couple of days, Faraday Institution in the UK have announced some groundbreaking funding of projects, and I noticed there was a couple of flow cell projects in there, so still sort of considered to be very cutting edge technology.
Yeah, I mean, a flow cell is it's an electrochemical device where a battery, all of the chemicals are stored inside the battery, and that limits the length of time that you can store the power. So it limits the energy part. With a flow cell, you store all the reactants and products externally in tanks. So if you want to increase the length of time that you can store the power, in other words, the amount of energy, you just make the tanks larger. So you separate the energy component from the power component, which makes a flow cell a very different class of energy storage device than a battery.
Okay.
Of course, the ultimate in separating power from energy is with hydrogen, because you use an electrolyzer and you don't store any of the energy inside the device. You store it in a tank or in the gas grid, or you provide it directly to an application. So for long duration energy storage, the ultimate separation of power from energy is electrolysis and green hydrogen.
Which neatly leads us up to where we are today. So you are the chief executive of this company, ITM Power PLC. Would you just like to tell us more about ITM and what you do there?
Sure. So ITM is an electrolyzer manufacturer. We manufacture PEM electrolysis equipment. We're a UK manufacturer. At the beginning of 2021, we moved into the world's largest electrolyzer factory with a capacity of 1 gigawatt per annum, and that's in Sheffield. It's called Bessemer Park. And the company raised 250 million on the London stock market to take us to a capacity of 5 gigawatts per annum by the end of 2024. So we're a world leader in PEM electrolysis equipment.
And actually, like doing it, you know, I was looking at some photos earlier. It's a big site that you've got there, and you're really producing units now already.
Yeah, I mean, we're shipping from the factory right now. There are many electrolyzer manufacturers who are startups or early stage companies who are making press releases about manufacturing and so on. We've been doing this for 20 years. We were the first hydrogen-related company on the London stock market, and we are shipping already from an existing factory. So this isn't about press releases. It's about actually producing kit and delivering it.
Cool. So, funnily, I was having a discussion with someone yesterday about electrolyzers, and we were sort of getting into the specifics of actually what is an electrolyzer. And to be frank, I probably did an awful job of answering that question. So I wish we'd had this discussion 2 days ago. But, you know, how would you describe an electrolyzer? What is an electrolyzer?
So an electrolyzer is a device that you use to split water with electricity to make hydrogen and oxygen. So, first thing to say is when you make hydrogen using electrolysis, if you use renewable power, then you have a fuel, hydrogen fuel, we call it green hydrogen, which has no carbon in its entire supply chain. Look, to pass a current through water and to evolve hydrogen and oxygen, you can't just pass the current through water because water is non-conductive. So what you need to do is you need to find a way, first of all, of making the water conductive.
Yep.
And the old way of doing that was by using a highly corrosive chemical called potassium hydroxide. Actually, the new way of doing it and the electrolysis that we have developed and we are manufacturing, it uses a polymer to absorb the water. And the polymer has fixed charges which allow the conductivity of protons. That's why it's called a proton exchange membrane electrolyzer, PEM or PEM electrolyzer. So the fixed acid groups on the backbone of the polymer are the thing that transport the protons. That makes the water, that means you can pass a current through the water and evolve hydrogen and oxygen. It also means there's a physical barrier between the anode and the cathode, which means you can make high pressure hydrogen, but it also means you can turn the electrolyzers on and off quickly, which means you could couple them directly to renewable power or use them to balance the grid. So there are massive advantages of having a PEM electrolyzer over older forms of electrolysis.
Okay. And when you're taking the water in to the proton exchange membrane, the PEM system, are you sort of atomizing the water, or is it a mist in airflow, or is it actual like a hose pipe of a tank of water?
Well, I'm not going to go into the detail of how we provide the water to the membrane because these are the sorts of things that we don't discuss. But,
okay.
It is water. It's clean water.
Okay.
You can use tap water. You need to clean the water before it goes into the electrolyzer, but we're using normal water.
Right. Okay. And then getting hydrogen and oxygen out. So, in terms of what kind of places are using these? So what's your customer base? Where's the pull coming from for these kind of systems? Because it's all, I think, and a lot of listeners of the podcast, we talk about electric vehicles a lot, and again, the discussion I was having the other day about electrolyzers and fuel cells and things, we were actually more talking about grid systems rather than mobile applications. And a lot of people get focused on the mobile side, but there's a whole host of things. There was a story in the news just yesterday about zero carbon bricks. So the first zero carbon brick, and it was also to do with hydrogen being used in the brick manufacturing process. So, where are you selling devices? What kind of customers are taking yours, and for what sort of applications?
So the entry market for green hydrogen is replacing carbonizing industrial hydrogen, which is made using natural gas. So the existing market for hydrogen is huge, and it's all in industry. 70 million tons per annum of hydrogen is used in industry.
70 million?
70 million tons, metric tons.
Bloody hell, that's a lot of hydrogen.
It's a lot of hydrogen. It's equivalent to 600 gigawatts of electrolysis. So that would be 6 centuries of the production of our gigafactory.
Wow.
And it is a massive amount of energy. It's all used to produce ammonia, and it's used in refining, and it's also an additional, on top of that, there's another 20 million tons per annum used in the form of syngas to make methanol. So it's a massive market. So there is a misperception of hydrogen that it somehow the market has to be created. Actually, the market exists already. So ammonia, for instance, let me give you an example. Ammonia uses about 35 million tons per year of hydrogen. Ammonia is made by reacting hydrogen with nitrogen, and the nitrogen comes from an air separation plant. And then ammonia is the world's fertilizer.
Yeah.
So it's one of the largest commodities on the planet. And all of the hydrogen that's used to make ammonia is produced using natural gas. And of course, you will have seen, as a result of the Russian conflict in Ukraine, the Russian invasion of the Ukraine, what has happened to gas prices. And that has directly affected fertilizer.
Yeah, and funny actually, a few people have said to me, why does gas price affect the fertilizer price? And I said, well, we make fertilizer from gas. And they, I think, don't realize, but you start to think about that. It's quite, that is a real basic input into the whole food system across the world. And obviously people are getting a little bit more aware of that now because of the Ukraine crisis. So going to green hydrogen in that would give you the opportunity to replace natural gas.
So look, all of that industrial hydrogen is made using natural gas. The price of natural gas now means that green hydrogen made with renewable power is a similar price to industrial hydrogen made using natural gas. So we've got to this incredible place where green hydrogen not only is net zero, not only gives you energy security, but it has parity with industrial hydrogen, which is used in huge volume. So it's an incredible moment to be an electrolyzer manufacturer.
Yeah, it is. You get the sense of feeling like your time has come, perhaps.
Yeah, I mean, we could see this coming for a long time. Actually, not the Ukraine crisis, but the need for a replacement for a grey hydrogen in industry. And of course, I've been doing this for 13 years now at ITM. ITM have been developing electrolysis for 20 years, and we've always understood that it's the only zero carbon fuel. It's nature's only zero carbon fuel. And it also gives you long duration energy storage for renewable power. And as you increase the amount of renewable power that you use, you need more and more energy storage. So it is absolutely essential that green hydrogen is an absolute requirement for the planet to get to net zero.
Wow, that's fascinating. So in a way, actually, all the sort of mobile applications and vehicle stuff that's kind of like a distraction over there, and really you've got these big kind of primary markets that you're focusing on to do with things like producing fertilizer or syngas. Syngas is another. I mean, the potential now for syngas must be enormous in terms of an alternative to fossil fuels, which can be put fairly easily into the gas distribution system.
So let me go back on something you said. I wouldn't say that transport is a distraction. We formed a joint venture with Vitol, a company called Motive, and that is directed towards refueling buses, trucks, and trains.
Okay.
So the place where hydrogen plays, there are two ways hydrogen play in the transport industry. One is pure hydrogen for fuel cell vehicles, where you're looking at heavy vehicles, transport vehicles, particularly trucks and buses. And the other one is the production of e-fuels. So, of course, ammonia is not only used for fertilizer, but ammonia, it can be used as an energy vector and a fuel, particularly if you're looking at marine fuels.
Yeah.
You can also make renewable methanol, and you can also make renewable kerosene. So you've got 3 e-fuels along with just using pure hydrogen. So it is very important for transport. The point I was making earlier is that actually the existing market is huge already. Okay. That is the market where many industrial companies are now buying large-scale electrolysis. That's why I called it the entry market.
Right. Okay. See. So there are. It's the beginning in a big space, and there's lots more coming in all of these new areas as well.
Absolutely. Yeah.
Wow. Okay. So you touched on a few things there with sort of synthetic fuels and aviation, which obviously. So kerosene is aviation fuel. People didn't know. So that's a huge sector that is in need of decarbonisation. Is, you know, air travel, the marine sector. That's another huge sector that's in need of decarbonisation, and really, really difficult to do. Those ships at the moment using horrible, basically road tar to run engines that produce lots of emissions like you wouldn't believe. So getting away from combustion engines in marine, or even to clean combustion in marine is really important, but certainly away from the awful fuel that they use at the moment. And again, that's an absolutely enormous space. So there must be there's a lot of things happening in the hydrogen economy at the moment, and I don't know. It feels like to me, like I quite often get drawn into this debate about how hydrogen basically isn't very efficient. So because you've got conversion losses when you convert electricity into hydrogen, then you've got conversion losses when you convert it back and use it again. And a lot of people will sort of argue with me that that because of that, it's a really inefficient way. It's a really inefficient energy vector, as you said. What do you make of that?
Well, I would say, first of all, very clearly, if you're going to drive towards net zero, wherever electrons are appropriate, you should use them. And wherever net zero molecules are appropriate, you should use them. You know, the efficiency argument, I have some sympathy with it for refueling small vehicles. But when you look at very large vehicles, there's a problem with that argument. Let me tell you what the problem is. It's to do with range and weight. So first of all, the efficiency argument, it goes something along the lines of it's more efficient to charge a battery than to make hydrogen and then use the hydrogen directly. That is the charging efficiency. Problem is this: if you want a very long-range vehicle, you have to use more and more batteries to increase the range. And when you do that, the batteries are carrying batteries. Yeah. And actually, the efficiency number is for charging. It is not for the overall vehicle. And you will find that if you try and get a truck and increase its range by adding more and more batteries, the actual efficiency that you see at the wheel goes down. Now, with hydrogen, you decouple the weight and the range. You just make the tank bigger. You don't need more and more heavy devices. And that's the reason why you use hydrogen for long-range, heavy vehicles like trucks and buses and trains. So the efficiency argument is a very tired argument that doesn't take into account the real efficiency at the axle of a vehicle that has a payload and requires the fuel and the energy on board to be as light as possible. So that's what I would say. But look, if you have a smaller vehicle and you're running around town, you're better off using a plug-in electric vehicle. I've got no problem with that at all. It's the same with large-scale energy storage. If you want 1 hour of energy storage for grid or load balancing, you're going to use a battery every time if it's 1 hour. But if you want 3 or 4 hours, you're going to use a flow cell. And if you want more than a few hours, if you want days or weeks or seasons, you're going to use hydrogen. So actually, there's a confusion about energy storage. You go flywheels and supercaps, batteries, flow cells, and everything from a few hours up is hydrogen. It's the same with vehicles. You know, if you want a blast of energy, you use a supercap. If you want regenerative braking, you use a battery. And if you want long range without the weight, you use hydrogen. And that's the reason that an advanced electric vehicle, because a hydrogen vehicle is an electric vehicle, an advanced electric vehicle has a supercap, a battery, and hydrogen with a fuel cell on board. It has all of those things. So you optimize the 3 technologies in one drivetrain. And the idea that it's one or the other is just a misunderstanding of what OEMs are developing.
Interesting. I think that's an interesting way of looking at it in terms of the duration, and obviously smaller vehicles don't tend to be operated for hours and hours on end. But the bigger the vehicle gets, and more sort of long distance commercial vehicles, or even rail, commercial vehicles, it's a funny, because actually they do have to stop quite often because driver brakes and rules and things like that. But trains don't. Like a freight train kind of runs until it gets to wherever it's going, and ships will run for weeks and weeks on end without the engine ever shutting down. So quite difficult in a case of something like a ship to implement a full battery electric.
So look, with a ship or a plane, one of the important considerations is being able to use the technology which already exists for the vehicle.
Mm.
So how do you do that then? So if you take a plane, for instance, which uses a standard aviation fuel like kerosene, you can make kerosene using green hydrogen. One of the world's largest projects for making renewable kerosene is our project with Shell at Rhineland Refinery, which is a 100 megawatt project making sustainable aviation fuel. Now, if you use the same fuel, but you make it as an e-fuel rather than a fossil fuel, you don't have to change the technology on the aircraft, which means, because redesigning an aeroplane, going through all of the trials that you need to do with the new technology in aviation takes a long, long time.
Yeah.
So you change the fuel, not the vehicle. Same with shipping. There are huge ships all over the world pumping out huge amounts of emissions, but those ships have a long lifetime with a lot of sunk capital. So again, what you do is you attack the fuel rather than the technology on the marine vessel.
Mm.
So you can use either an e-fuel based on ammonia or based on methanol. And you do the same thing as you do in aviation. So you go, it's to do with range and weight. You start with a small runaround vehicle, it's going to be plug-in electric. You go to a large commercial vehicle, it's going to be hydrogen with a supercab and a battery on board. You have to have a battery because you need regenerative braking. And then a very long range, very large vehicles with technology that's difficult to replace, you use an e-fuel.
Yeah, fascinating. So in that kind of case, the benefits there are potentially massive with things like shipping and aviation, because they are like very long way away from anything like electrification, like ground-based applications are, and particularly shipping is one of the real big hidden, not so hidden, but it's sort of it's a nationless problem in shipping, because it's sort of a way on the oceans transporting goods around, so absolutely essential to the global economy, but we don't see it, and the pollution that comes off marine vessels is horrendous. It's not just CO2; it's all the other horrible stuff they throw out, or sometimes scrub out of the exhaust and dump straight into the sea, ironically, to shortcut the process. So even just having a clean, synthetically manufactured fuel, without all the sulfur and all the other horrible stuff in that marine fuel currently has, would be a big opportunity for that industry. The thing that kind of tends to drive them, though, is cost. Do you see the costs of sort of syn fuels and things intersecting with that kind of thing, or is it going to take, will it need to be sort of forced by legislation? How do you see that economic working out?
So my first answer would be, what's the cost of not doing anything?
Yeah,
the cost of not doing anything is a continued environmental crisis, which is posing an existential threat. So the cost of not doing anything is far larger. The energy transition isn't going to be free. Just absolutely is not going to be free. And governments need to decide how they drive forward with it. what the policies are, what the incentives are, and also there's a carrot and a stick, and there needs to be legislation against pumping out all of them. So there's a whole range of things that needs doing. You look at the cost of not doing things. So you look at the cost of strange weather events. You look at the cost of, and not only looking at the cost from an environmental point of view, also look at the cost now of fuels and what's happened since. Not only has there been a massive increase in the price of natural gas, which we talked about, but what about the price of Brent crude? What about the price of oil? I mean, it's a very topical subject about fuel, but yesterday the EU announced that it was not going to continue using Russian oil apart from pipeline oil. I filled up my car and I saw the effect. We all see the effect of these things. So I think we need to be thinking about what the reality is today, about, first of all, entering an energy crisis and energy security crisis, which we're in with the Ukraine situation, but also an environmental one at the same time. And there does need to be legislation, and shipping is key, as is aviation.
Yeah, a huge part of the problem. So just to kind of get it into context, you mentioned earlier the current market for industrial hydrogen was 70 million tons per annum. And, when we're looking at these different applications of, a truck or a train or a marine vessel, you can store an awful lot of energy in a kilogram of hydrogen. Do you know roughly something like a long haul truck or a train, how much hydrogen are you talking about that something like that would use in comparison to that 70 million?
For some numbers, let's start right from the top. So in the UK today, let's just take the UK because the sizing is easy. So we use 300 terawatt hours of energy flowing through our electricity grid. We use 600 terawatt hours of fuel. And we use 800 terawatt hours of natural gas for heat. So if you go electricity, fuel, and heat, you go 300 terawatt hours, 600 terawatt hours, 800 terawatt hours. Actually, the amount of heat, the amount of gas, natural gas flowing through the gas grid used to be 900 terawatt hours, which made it easier because it was a ratio of 1 to 2 to 3. but fuel is 600 terawatt hours today. Now, in terms of the amount of hydrogen you use, if you want to move to a renewable energy network where you just have renewables and nuclear in the electricity grid, you supply all of your gas grid with its needs from hydrogen, and also have a mix of electrons and hydrogen in transport. You're looking at a requirement, and this assumes some energy efficiency improvement, but you're looking at a requirement in the UK alone for between 30 and 50 gigawatts of electrolysis to do that. The IEA says that the world needs 3,500 gigawatts of electrolysis to get to net zero. 3,500. And that all has to be deployed in 28 years, before 2050.
So we've got 30 to 50 gigawatts of hydrogen generation needed in the UK. That sounds like quite a big. That sounds like quite a big number.
It is a big number, and if you read the IEA report on the roadmap to get to net zero by 2050, it says that the world needs 3,500 gigawatts of electrolysis. That's, Ryan, is equivalent to running the world's largest electrolyser factory, which is our gigafactory in Sheffield, for 35 centuries to make that amount of electrolysis. And the world needs that in the next 28 years. Our target in the UK, our target for the next 8 years is 10 gigawatts, 5 of those gigawatts being electrolysis. So that's the existing target announced by the UK government, 5 gigawatts in the next 8 years.
Wow. So presumably we're going to need to see an acceleration of implementation after that. Are you getting the sense that that's coming, that the pace will start to quicken?
Yeah, we certainly are. I mean, we have a plan and we've raised enough money. We raised 250 million on the London stock market last October, and we will get to 5 gigawatts per annum of manufacturing capacity by the end of 2024. And we alone will be able to manufacture the amount of electrolysis that is required by the UK government in the next 8 years. We'll be able to do that and manufacture it in our factories.
Okay. But you don't just supply the UK, do you? You are an export business. You're supplying other countries as well. So
today we have 499 megawatts of backlog, which is about half a gigawatt, and all of it is outside of the UK, apart from about 20 megawatts. So nearly all of it is outside of the UK. It's all export.
Wow, that's I'm getting confused in my head between my megawatts and my gigawatts there. So you're about half. So yeah, okay. So in terms of your planned capacity, actually, you're going to be able to deal with that. It's not like you're backlogged for the next 5 years. But you've got a healthy order book. I think that's what we're trying to say.
We've got a healthy order book, and the order book is increasing in size all of the time. It's a very, very dynamic market that we're in. And we work very closely with Linde Engineering. Linde Engineering are the world's largest employer of industrial hydrogen. They have 30% of the world market for industrial hydrogen. They are our strategic partner. We formed a joint venture with Linde for deploying electrolysis, particularly for industry. And we are developing projects all over the world. So things are moving very quickly, Ryan.
Okay. I was going to ask actually about that sort of thing in terms of what we're kind of seeing as we shift away from fossil fuels to new energy sources. Often brings with it an opportunity to kind of change the supply chain. So the way that a company will do something, they might locally generate their electricity, for example, or locally produce gas, nitrogen or whatever. Is that sort of thing happening with hydrogen as well? You would move it to the point at which it was being used, and you'd put a system in?
When you do a hydrogen project, you deploy the electrolyzer where the demand is for the hydrogen. You don't build an electrolyzer. Build and the people will come doesn't work. For instance, the demand centers are refineries and ammonia production. They're the two demand centers for industrial hydrogen. So we work with Shell, for instance, at the Rhineland refinery, with Phillips 66 in the Humberside in the UK, and with Total at Leuna in Germany. And we are putting the electrolyzers right next to where the hydrogen is used at those refineries or chemical plants. And in terms of ammonia, we're working now with Yara, and we are deploying electrolysis equipment right next to the ammonia plant. So that's the way you do it. You take the electrolyzer to the demand center and supply it directly.
And that would obviously has some system level benefits in terms of not having to move large quantities of gas around as well.
Yeah, you wouldn't want to truck industrial hydrogen around because you use such a huge quantity of it.
Yeah.
I mean, the hydrogen today that's used at refineries and for ammonia comes in via a gas pipe and goes through a reformer, and it's still methane reformed.
Yeah.
The difference now is that instead of using a reformer, you use an electrolyser, and the energy comes in from the electricity grid, not the gas grid.
Right. So, and then in terms of how the UK is doing, you've obviously mentioned some targets there from the UK government in the long term and in some somewhat shorter term, and your plans. Is there a particular market or country where you see the strongest pull? Is the UK up there? Are we doing enough in the UK, do you think? Or how does that look globally?
Well, recently the UK doubled its hydrogen target from 5 gigawatts to 10. So that was progress. I think also the hydrogen strategy, which, by the way, was announced at our factory by Kwasi Kwarteng, who's the Secretary of State for BEIS. There is a strategy that exists that is being updated with a business model, which we will see in the next couple of months. So that's an important moment. We're also have an RTFO, that's a renewable transport fuels obligation, and actually reforming that for hydrogen. That is in consultation, and that will be announced soon as well. So there's some very important things to come from the UK government. But are we ahead of other places? Europe is moving ahead very, very quickly, particularly Germany. And our partner Linda are in Germany. And we have a company called ITM Power GmbH in Germany. And we recently received some German grant funding for some large projects in Germany.
Okay.
We're also interested in Australia. We're interested in Chile. We're interested in the US and also the Middle East. So a lot of regions now moving very quickly.
Oh, okay. Interesting. So I think we're at 45 minutes already. So I'll just bring it to a close now. So looking into the future with your crystal ball, as you do, but looking ahead, next 12 months, 36 months, what are the things that have got you the most excited about what's happening with ITM Power and the industry in general?
So I think green hydrogen is without a doubt finding a place in the energy transition, particularly now with energy security as well as net zero. I think policymakers are discovering that hydrogen is not only about net zero and energy storage, also about energy security. And the cost of green hydrogen has come down as the cost of industrial hydrogen has gone up. So we've got all these very powerful arrows which have all clicked into alignment over the last 6 months. And I see a lot of policy being developed to incentivize green hydrogen all over the world. So it looks to me like an incredibly positive year is about to come.
And do you think you will be able to scale the business up quickly enough? I mean, you've got this huge, you've got this great investment now, but do you think you're going to be able to scale quickly enough with all the other things that are going on in the world at the moment?
Yeah, we do have the backing of the City of London. They have a fantastic understanding now of green hydrogen and energy storage and so on. I feel absolutely confident that we'll be able to implement our plan. Will it be enough? Possibly not. I think we'll be capacity constrained, and that's a better problem to have than a lack of interest. I mean, the amount of interest in green hydrogen from industry now is absolutely phenomenal.
Brilliant. Okay, well, and that's been absolutely fascinating, Graham. We've come to the time there, so we'll draw it to a close. But brilliant. Thank you very much for taking a bit of time out to talk to me today. And I hope, I mean, I've certainly got a lot from that in terms of understanding a bit more about the hydrogen economy and how much more depth there is to it. Hopefully people listening will as well. Hopefully see a few less arguments on my kind of social media chats about it. So great. Thank you. It's been really interesting.
No, thanks, Ryan. Thanks very much for having me. And thank you to everyone out there for listening.